sequence, Fibonacci. The Fibonacci sequence is equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2 for all number bigger than 1. If you try to implement the Fibonacci directly, you will get an exceptionally slow code. Your code will be divided in two parts. An if that check for the number bigger than 1 and just return 0, no problem there. And a body. And the body where we are calling in Fibonacci twice. One for n minus 1 and one for n minus 2. This will make the computation exponentially expensive because every level down we will split in two very similar computations that will go and split in two again and again and again, exponentially. Fibonacci is one of the iconic use cases of lazy caching, the topic of today. If we create a compute Fibo class with a field number that is the number for which we want to compute Fibonacci, and the method that actually computes Fibonacci for that number without taking any parameter, we can annotate this method with cache.lazy, and it's now going to be computed only one time for each structurally equivalent object. This means that those two calls are going to be cached when we actually call them, and so they are just going to return the value of the computation as if they were accessing a field instead of recomputing the whole thing. We can have a main that run our compute Fibo for 42, and we can press run, and in just a moment you will see a result. If we were to remove the cache lazy annotation and try to run the code again, the code will basically run forever. It will be so slow that will never actually compute because 42 exponential is an absurdly giant number. Hello! Today we are going to see caching. Caching is the general idea that you want to do the same thing over and over again. A particular case of not doing the same thing over and over again is about not creating the same identical object over and over again. That is, if two objects are structurally equivalent and immutable, they could very well be the same object in memory. This is obtained in 42 with the concept of normalization. Normalization in 42 has to be asked by the user. So if you just create your immutable object, it will be a new object, even if a structurally identical object already exists. But if you call norm from data, then you will get the normalized version of the object. So if, for example, you create two different bobs, bob 1 and bob 2, and then you do bob1 colon equal bob1.norm and bob2 colon equal bob2.norm, now you will only have one bob object in memory that represent both of them because they are structurally equivalent. Data allows you to take parameters to ask for your immutable classes to directly create normalized objects. For example, call data in this way with autonorm equal true, and all your bobs are going to be normalized from the beginning, and just calling an extra .norm will just be a no-op, and it's a pretty fast no-op. So if you are not sure if an object is normalized, calling norm is a very fast operation. Normalizing an object also normalizes the whole reachable object graph. So you don't necessarily have to keep calling norm continuously because you're very worried what's happening. If you have your result that is meaningful for you and you want to normalize this object and the whole arbitrary complicated reachable object graph that includes private sub-object that you don't know or control, you just call norm on the top level object that you can see. We can see this in this slightly more complex code where in addition to the persons we have dogs, and the idea is that the dog can be owned by a person. And so here we can have bob1 and bob2 that for now are two different bobs in memory, and then we can have dog1 equal dog of Grontos owned by bob1 and dog2 of Agrajak owned by bob2. And well, dog1 owner is a different object with respect to dog2 owner. They are structurally equivalent, but they are different objects. And yes, we cannot tell them apart in 42, but if you observe the memory consumption, you may see quite of a different bump. Then we can call our norm on our dog. So dog1.norm and dog2.norm. The two dogs are different objects because they have different names, and so they will stay different. But since the normalization goes deep inside the reachable object graph and normalize everything reachable, now the pointer of the owner have been normalized. So dog1 and dog2 actually have the same owner, the same object in memory. So if we somehow forget about Bob2, Bob2 could be garbage collected, because dog2 is not referring to Bob2 anymore, it's actually going to refer to Bob1. This technique to normalize objects so that we can keep less objects in memory because we just keep a single copy for each structurally equivalent variant is actually the key to unlock a lot of other kinds of caching. We motivate lazy caching using the Fibonacci function, a very famous mathematical function that if you try to compute it in a naive way will take basically forever to run because it's calling itself twice in its execution. That is, if you implement slow Fibo like this with an if n is 0 or 1 return n, otherwise call recursively slow Fibo of n-1 plus slow Fibo of n-2, this will take forever to run even for reasonably little values of n. With cache lazy, instead, we can avoid recomputing Fibo over and over again. We can automatically recognize where certain values for Fibonacci have already been computed and just return the result. To do so, we piggyback on the idea of object normalization of before. So we make an object that represents a computation for Fibonacci. This object will need to have as fields the arguments for our Fibonacci function, that is just the number that. Then we can have an immutable method that returns a num and have the empty name that is annotated with cache lazy. And in the method we basically repeat the body here in line 2 or 3 or our slow Fibo. That is, we extract the field and we call it n, and then if n is 0 or 1 we just return n, and then we take a local variable Fibo1 that create an object of type compute Fibo for n-1, and then we return Fibo1 open close, that is, please compute Fibonacci for n-1 plus a new object with n-2, and again please compute Fibonacci for n-2. Those are newly created objects, so it may seem like the information for that Fibonacci number is not available in the system. This is where we piggyback on object normalization. Every time we call a cache lazy method, we actually first normalize the object and then check if this method has been called on the normalized version of this object. In this way, we will basically have an automatically populated cache of all the possible values of Fibonacci that we have already explored in our execution, and we will just access the existing result. That is, we will be able to call our compute Fibo 42 open close and get the big number in a reasonable time. If we were to remove cache.lazy, we will perform logically the same computation, but it will take an absurdly long amount of time to compute. That is, in 42, cache lazy guarantees semantic equivalence. There is no way to write code with cache lazy that get a different result if you remove cache lazy. Your only difference will be performance. Cache lazy is only a way to produce faster code. The language guarantees that there is no way to get a different result. This is different from other kind of cache support that you can find in some other language. For example, in Python, you can have an annotation to set your slow Fibo as a cached method, and it would make your slow Fibo work at a reasonable speed. But only if you have actually made your slow Fibo a fully deterministic method. If you failed and your slow Fibo accidentally is a method that taking input something instead of just those immutable parameters and can possibly produce different results in different moments, then those other kind of caching support that you can find in a couple of other languages will just produce the wrong result. That is, they will silently fail. You will get a program that will do the wrong thing. Here we are showing a way to do cache lazy with these computation objects. When you want to do a computation from some immutable parameters into an immutable result, you can always just create an object that has those parameters as fields and have an extra method that you can call compute or just the empty method name that uses the field instead of the parameters to produce the result. This is admittedly a little bit more involved with respect to just being able to annotate the method slow Fibo directly. And I could have just made the language so that you could just annotate slow Fibo directly. More than that, a user of 42 can write a library class that will allow you to have cache lazy by just annotating the method directly instead of having to pass through the computation object. So why, Marco, why you are publishing the language in this state where we have to make the computation objects or to make this abstraction ourselves? I think that the computation object is a great abstraction to learn, and it scales to way more special cases. That is, there is so much more that you can do with caching once you are comfortable using this computation object pattern with respect to what you can do by simply caching the execution of a specific method. In particular, the next topic here is automatic parallelization. Yeah? What is automatic parallelization or parallelization in general have to do with caching? Actually, quite a lot. You see, when you do caching, you are basically reusing a computation that happens before in time, because you know that there is no inference between this computation that you will repeat and the old computation that you have done. And in order to do automatic non-observable parallelism, you need exactly the same property. That is, if you know that two computations do not depend from each other in any way, they can be run in parallel. Also, coming back to the computation object of before, if you create a computation object, all the information to compute is already in the object. So with cache lazy, we start the computation when we call the method the first time. And instead, with cache eager, we start the computation as soon as the computation object has been created. In this way, if we make, for example, two different methods, is polite and is grammatical inside of a task class that have a text field, those two methods will be able to use the text field to check if this text is polite and to check if this text is grammatical. And if we annotate those methods with the cache.eager, they will start computing the result in parallel when a specific task object is created. So in this way, we are actually spawning two workers and let them work on those two problems in parallel. Moreover, we can make a list of tasks, and we can initialize the various elements of this list with various newly created task objects. And whenever we create any of those task objects, they will start computing the result. Then they enter in the list, and if we iterate on our elements in the list after all the elements have been created, we will basically do a conventional fork join over the list, where we will basically initialize our tasks by filling the list. We will then wait for all the tasks to be completed, and we will read all the tasks one by looking to the elements of the list. And all of this in 42 just look like filling up the list and reading it. And again, if I were to remove the cache-eager annotations, absolutely everything will stay the same except for performance. Now, be careful to not over-parallelize. If you put too much parallelism, you may end up having a slower program than what you started with. Parallelism is great, but only when your machine has latent parallel computing capability. If you are already in a setting where all your cores are being used, adding cache-eager may slow down your application, but the behavior is going to stay the same no matter what. That is, just to be clear, because some people think it's going to stay the same if you do some, good programming, if you import only trusted libraries. No. In 42, even if you step out of the language and import a broken C library that goes in undefined behavior, the semantic of cache lazy and cache eager still preserve the semantic that you will have without that annotation. We will go in the detail on how that works in the future, but if you don't believe me, try to break it. Try to break 42. Show me some example where you actually get a different behavior if you have the annotation or not. And then we go to invariance. Invariance? Marco, but this is the caching chapter. How is that you managed to talk about parallelism and invariance? Well, actually, also invariants are related to caching. A derived field is a field whose value is fully determined from the value of some other fields. So, for example, we can have a class point that is a data class with three fields, x, y, and distance from origin. And clearly the distance from origin is completely determined from x and y. So how could we do this? Well, in a conventional language, we could have a manually defined factory that just takes x and y, and then we initialize x as x, y as y, and then distance from origin as the corresponding computation that generates the right distance from origin. If you write code like this, you leave your program open to abuse. That is, someone else could call the default factory that takes x, y, and distance from origin and creates an invalid point object. And if you are thinking that you will just not call that method, you are not thinking like a programmer that works in a group. You have to be sure that there is no way your code can possibly be misused. You need to make sure that your code never ever does the wrong action. And creating an invalid object is clearly a wrong action. So, if this is not the right solution, what can we do? Well, we can use cache.now. That is yet another kind of cache that is computed in the moment the object is created. So, cache.lazy is created the first time you call the method. Cache.eager starts to be computed in parallel as soon as the object has been created. Cache now is even earlier. It's created at the same time of the object. In particular, the object itself don't exist yet. So the cache now method cannot be a method of the object, need to be expressed as a method on the class, and then data turns that method into a method on object. That is, you define a method that is a class method with the name you want your instant method to be, and this method will take two extra parameters, in this case x and y, that have the same name of the fields. So you will pass the value of the fields as parameters. And then in the computation of the method, you just describe how this new field, distance from origin, is actually connected with the value of the other fields, and data will make sure that there is no way you can have an object where x and y are not perfectly synchronized with the value of distance from origin. This same pattern allows us to talk about invariants that are sometimes called class invariants, representation invariants, object invariants. That is, you can express the fact that all the instances of a certain class need to have a certain property. And you write that property. So it's an exceptionally expressive way to guarantee that your code do exactly what you want. It's a very, very expressive way to force your code to behave as expected, because you can take any object and you can write any property over its fields, and this property will always hold. If you attempt to create the object with bad values for the fields, your invariant will just fail and the object will not be created, so there will never be a wrong object in the program. So, for example, here in point, we can have our x and y, we can have our distance from origin double, and we can also have a method invariant that take x and y and is a cache now and return void. So this is the main difference. The distance from origin, that is the derived field, returns a double the value of that field, while invariant, that is just a property on the object, returns void because there is no corresponding meaningful value to return. Or, if you prefer, a synthetic field of type void that thus doesn't even need to be generated and occupying space can be used to represent an invariant. To implement the invariant, you can just make a check, and if the check fails, throw an error. So, for example, you can have if is not the case that x is bigger than 0 double and y is bigger than 0 double, error x multiline string invalid state where x is x and y is y. Or, if you prefer, you can just write x where this have to hold and the message is the string with the invalid state. Whatever you prefer. You can have the explicit if, you can have the x directly. In both cases, if the check fails, you get an error. And so, since the cache now is computed during the object creation, you will never actually return the object. Concluding, in 42, we have those three kind of caches. cache lazy, cache eager, and cache now. And those three caches just computes the value in different way and in different moments. Cache lazy computes the value the first time the method is called, and then every time the method is called again on a structurally equivalent object, we will just get the same result back without the need of recomputing it. Cache eager starts computing the cache in parallel with the rest of the application as soon as the object is created. So if you create the object and you just call the method directly after, it will basically behave like cache lazy. But if you create the object and you wait a little bit because you're doing other things, then when you call the method, the cache could have been already completed for you. Cache now then compute the cache as early as possible. The object cannot exist if the cache is not there ready. And in this way we can encode invariants so that you can make an arbitrarily complicated property and make sure that all the objects of a certain type actually respects that property. Today we have just looked at to cache for immutable objects, but this is not all that 42 have to offer. Next time we are going to see how to do caching on mutable objects. So see you next time!